sit in the PhD meetings, every other day they come up with the new problems. So one day they say microplastics, the microorganisms, a lot of challenges it is emerging every day. So this type of seminars will be of great help to disseminate the knowledge. I congratulate the organizers for arranging this wonderful event. So I'm also very glad that 3 universities, top universities in the world, have joined hands to organize this seminar. So I just checked the schedule. So 9 interesting topics are lined up over a period of 5 years. So sufficient time is given to each seminar so that the discussions are all fruitful. So I'm sure that the deliberations will be very useful to advance our knowledge in the area dealing with the wastewater. I wish this seminar a grand success. So as this is online, we could not give you our hospitality. So please do visit us whenever you get a chance. Our campus is one of the beautiful campuses in the country. We also are very conscious about the environment. So we have a 4 MLD sewage treatment plant. We get the advice from Madhav, Liji, and other colleagues dealing with the things. We have the dual pipeline system. We try not to waste even a drop of water. So the freshwater requirement now has drastically came down after implementing this new technologies. And we also are very conscious of preserving the forest. Ours is a forest with footprint utilization of only about 25%. So remaining area we leave to nature, and those who have not visited, please do visit us. You will be greeted with deers, blackbirds, and many other beautiful flora and fauna. So with these few words, I wish this seminar a grand success. Thank you.
Thank you, sir, for giving such a warm welcome speech that was articulated so well. Now, proceeding our ceremony, next, I would like to invite Dr. Prachi Kaul. She is the director of Shastri Indo-Canadian Institute. She has been associated with the institute for more than 16 years now. An alumna of IIT Delhi, Dr. Kaul has served to international and national bodies before joining the Shastri Institute. She is a social scientist with keen interest in studying aspirations and social mobility of the masses and its relation to higher education. Dr. Kaul serves on the advisory boards of a couple of academic and research institutions and joint working groups in between India and Canada on different domains. With this brief intro, now I welcome Dr. Prachi Kaul, Director of Shastri Indo-Canadian Institute, to deliver the presidential address.
Good evening, everyone. Thank you so much for having me here with all of you. It's not a presidential address by any means, I would say, because I'm not a domain expert here. But it's a pleasure and it's a delight for me to be with all of you today, joining you in the inaugural of this wonderful event that Dr. Kumar and his team has put together. Which is supported by Shastri Indo-Canadian Institute, and we take pride in being associated with this institution, which is IIT Madras, and also with University of Calgary, which is another institution on board from both the ends. And this particular event is being organized and out of the research that they have been carrying out. Of course, as a team, there are 2 other institutions joining from the other world, but here I'm talking about India and Canada and the mandate that I carry along with Shastri Indo-Canadian Institute. Those present here, I assume that some of you would be aware of Shastri Indo-Canadian Institute's activities and mandate it carries with it. But those who are not aware or not are partially aware, I would say that we are binational organization mandated by Government of India and Government of Canada at both the ends. 2 offices, one is in New Delhi, one is in Calgary, in fact. And we are very pleased to share with this community that we are actually housed in University of Calgary premises itself in Alberta province. We operate bilaterally, and what we do is the facilitation, and the facilitation can be done by 2 ways in terms of supporting the academia and research fraternity from institutions that are part of our network. As you may or may not be aware, but Shastri has 180 prestigious institutions on board right now. And you name a good university or institution here in India or Canada, you will find it on our board from India, Indian Member Council or Canadian Member Council of the Institute. So we are facilitating the collaboration 2 ways, primarily. And the first one I would say is by providing some financial assistance to carry out research or academic activities. I'm very pleased to say that there's no segment of academia or research that remains untouched by Shastri. In terms of mobility programs, we have opportunities for undergrad students to go to Canada. Similarly, Canadian students to come down to India and be associated with institutions like IIT Madras or any other organization that is interested in that. To grad level student mobility, to doctoral to postdoctoral level as well. We also facilitate mobility of faculty members, whether they are young or they are established. We bring together people who are interested or who can provide each other a complementarity on any area of research that they deem appropriate to take forward. And this is one example of that program that we offer, which is called Shastri Institutional Collaborative Research Grant. And they are the proud recipients. And I am proud manager, as an administrator, I would say I take pride in saying that they are recipient and they are doing wonderful work in the area that is very, very important, I would say vital to sustainable development goal. As we all know that water, clean water and sanitation is marked as 6th SDG goal by UN, and Shastri Institute have been quite instrumental in building its narratives, building its workings around sustainable development goals. And this remain in high in priority for our organization to directly work in the area or indirectly by supporting the work that our institutions are doing. And this is one example to cite here. I am, as I said, that I am no domain expert, but as a lay person, I can say that water is remains in the core of our sustenance. And there are some statistics that I could see over internet, and I was kind of shaken inside. We have been talking about climate change, and we have been talking about the repercussions that we are already into it, and we are seeing ways and patterns of our life, how they are reflecting. And I was surprised to note that around 733 plus million people currently live in countries with high and critical level of water stress, which means it's a really severe state of affairs. And if we talk about the current rate, how badly we are exploiting our resources, and by 2030, I think, if I'm not wrong, around 1.6 billion people probably be lacking safely managed drinking water, and around 2.8 billion people will lack water for sanitation, and similarly around close to 9 billion people would lack in terms of access to hygiene facilities. So we can imagine how in the peripheral in a way how peripheral effect of this lack of sanitized water are going to bring to our society. As a person, I feel very much responsible towards creating an ecosystem that can support not just our community, but the whole world's community as well. We as a parent, we as a civilian, we as an individual share the equal responsibility to hold it tight and hold it dear to us. And we all should carry it strongly. I think each of us need to do our bit by saving even a drop of water that is possible. There can be a number of ways to implement it at our place by making our children aware of it and by learning from them. They are the next generation. I think they are very smart people. Young humans are very, very intelligent people. I think there's a lot to learn from their side. And I think if we can create an ecosystem by which we can ensure that a system which is similar to IIT Madras that our dear Professor Johnson has talked about, by saving and nurturing even a single drop of rainwater or recycling it for the other purposes, so that the weight on the current supply of fresh water is limited, and we would be able to sustain for a longer time. And replenish the resources as well. And whatever is needed to do that can be researched and taught by this wonderful community that is present today. So I wish you all the very best for this particular seminar. I am sure, and at the beginning of the seminar, I was just trying to check with Dr. Kumar how far we have reached and what is the kind of engagement that we are having right now. Very pleased to understand there's already mobility of students happening, and I'm sure their presence in, whether it is in Canada or Sydney or any other place, I think they are going to learn from each other. They are going to share their enrichment with each other, and they are going to grow and foster a community which is like-minded and which is working passionately for the cause this seminar is being organized. Thank you so very much once again for inviting me for this particular session. I wish you all the best, and I wish that this work doesn't end with this particular research project. And there are ways to engage with Shastri further as well. So please keep exploring the opportunities through Shastri and through other mediums, but work should continue and work should be done for the betterment of larger community. Thank you so much once again, and have wonderful deliberations throughout. Thank you. Namaskar.
That was quite insightful, ma'am. I appreciate your concern and efforts towards our environment, making it a safe place to live. We are so proud of you, Dr. Kaul. You're absolutely a true example and face of the women empowerment. Thank you, ma'am, for remarkably addressing us today and inspiring us. Now, I'm also delighted to have here with us today distinguished Professor Ho Hao No. Hao is an award-winning and world-leading researcher in environmental engineering. He is also a distinguished professor of environmental engineering and deputy director of the Center for Technology in Water and Wastewater at University of Technology, Sydney, Australia. He is also co-director of the Joint Research Center for Protective Infrastructure Technology and Environmental Green Bioprocess. So, on behalf of one and all present here, I welcome you, sir, to deliver the inaugural address.
Thank you so much for your guys' introduction. Dear respectful participants, ladies and gentlemen, I'm so honored and delighted to have a chance today for giving an inaugural address for the International Seminar on Advanced Technologies for Wastewater Management, which is organized by Professor Kumar, IIT Madras, and associated with University of Technology, Sydney, and University of Calgary, and sponsored by Sastry Indo-Canadian Institute and SPARC MHRG Government of India. I'm very pleased to know this ATWN seminar has successfully attracted more than 200 participants. I do wish to attend. My heartfelt congratulations to the open ceremony this afternoon. As you know, advanced water and wastewater treatment technologies aim to reduce level of impurity such as organic matter, nutrients, and toxic pollutants, etc., from water and wastewater. While emerging pollutants like pharmaceutical and personal care products, endocrine disrupting substances, pesticide, surfactants, household chemical, and so on are synthetic or naturally occurring biochemical entities in the environment that are not monitored or regulated in most cases, but as adverse effects on human health and ecosystem. Emergent pollutants are mainly removed in secondary treatment via a range of processes, including dispersion, dilution, partition, biodegradation, and abiotic transformation. Algae-based technologies have been utilized for the treatment of wastewater containing organics, nutrients, and emerging pollutants, which provide numerous benefits, including efficient fixation of carbon dioxide, low environmental impact, solar energy driven activity, and production of renewable sources as feedstocks for generation of biofuel or other value-added products. Advanced oxidation processes have many merits, such as rapid reaction rate, small footprint, high potential in reducing toxicity of organic compounds, mineralization of organic disinfection, no generation of concentrate waste for further treatment, and no sludge production. Nevertheless, their further applications are hindered by the relatively high capital and operating or maintenance costs, tailoring of complex chemistry to specific contaminants, and requirement of quenching of residual parasite. Although membrane technology can improve effluent quality, membrane fouling is the major obstacle for its application in wastewater treatment. Therefore, combine these technologies is required to integrate their advantages while minimizing their respective drawbacks. Consequently, the combined technologies will be more effective in removing organics, nutrient, emerging pollutants, heavy metal, pathogen, and bacterial from water and wastewater than the single technology, okay? Thereby significantly improving effluent quality for sustainable water management. This seminar covers on the major aspects which I have just mentioned. It focuses on development of novel membranes, surface modification, and functionalization of existing membranes to improve selectivity and resource recovery. Development and deployment of novel advanced oxidation processes for wastewater treatment. Algal photobioreactors for treatment of wastewater to remove emerging pollutants and toxic metal ions along with production of biofuels, bioplastics, and other active compounds. The last item is hybrid system comprising algal, membrane, and advanced oxidation system to sustainable manage wastewater. Finally, I would like to extend my warmest welcome and gratitude to all for your attendance and support, and sincerely wish the ATWN 2022 great success. Thank you so much for your attention and goodbye. Thank you so much.
Thank you, Professor Howe, for inaugurating this international seminar for us and enlightening us with the intricacies of this seminar. Now, I would like to invite Dr. Madhava Kumar on the virtual stage for giving the vote of thanks. Dr. Madhava is an Associate Professor, Environmental Engineering Division, Department of Civil Engineering, IIT Madras. He is also the coordinator of this event. Sir, now I'll request you to kindly take the lead.
Yeah, thank you very much, Son. It's my pleasure to deliver the vote of thanks on behalf of the organizing team of ATWM 2022. First and foremost, I would like to thank the Shastri Indo-Canadian Institute and the Spark MHRD India for supporting the seminar through the 2 ongoing international projects. And I also very grateful to Dr. Prachik Kaul, the Director, SICA India, for taking your time to deliver the presidential address in spite of your very busy schedule. Madam, I would like to mention here that SICI is one of the agencies to give the reply immediately for any queries within the same day. I really appreciate with your leadership that's going on. I have really very pleasant working experience with your office too. I also take this opportunity to thank Dr. Reshma Rana and your office for their kind support. From the bottom of my heart, I thank Professor Hu Hao No, Distinguished Professor, University of Technology, Sydney, for delivering the inaugural address and also for delivering the invited lecture shortly after this inaugural event. I thank Professor Robinson, Head, Department of Civil Engineering, for accepting our invitation to deliver the welcome address. Sir, thank you very much for your support and encouragement as a head and a colleague in the Department of Civil Engineering, IIT Madras. This is not possible without the help of team of experts working in line with the United Nations Sustainability Development Goals, SDG 6, as Professor Kaul rightly mentioned, clean water and sanitation. I thank Professor Gopalachari, University of Calgary, and Professor Hu Hao No from UTS, Australia, for coming forward to coordinate this international seminar and providing excellent support for me from the day one of this proposal. Thank you, Professor Howe, and thank you, Professor Gopal. Connecting from east to west in the time zone is very tough task for us, and we made several meetings to fix the time of this event, and we just gave little relaxations for the speakers. I'm extremely thankful to all the speakers, Professor Chia Hong Ho from National Taiwan University from Taiwan, and Professor Samir Kanal from the University of Hawaii, Mano, Professor Chandra Tikala from the Louisiana State University, USA, and Professor Tek Tay Lim from Nanyang Technological University, Singapore. Professor Lim is already here, but we could not able to hear him during the inaugural event. Professor Wensan Gao from the University of Technology, Sydney, Australia, and Dr. Kuang Fu from the University of Technology, Sydney, and all the project team scholars, especially mentioning Sairan Fang from UTS, Australia, then Sajat from the University of Calgary. We know that it's extremely difficult to adjust with the time zones. We are really sorry for the inconvenience, but you readily agreed to give the lectures in this seminar. I also place on record my sincere thanks to the Global Engagement Office at IIT Madras for their help and support in the day one of their seminar proposal. Also, I thank Communications and Public Relations Office as well as the Media Cell of IIT Madras for providing the publicity and live streaming of this event in the official YouTube handle of IIT Madras. My sincere gratitude to all my faculty colleagues in the department and in the institute for their kind support and encouragement for arranging this seminar. I also thank all the staff members who are directly or indirectly involved to this particular event. Our honest thanks to all the participants who registered in large number. I could see only like 109 turned up now, probably because of the semi-final match which is going on between India and England now. Probably I expect them to join at least from the lecture 1 onwards. And the registration gives us the required energy and enthusiasm for arranging this a little more in a final manner. Finally, I thank all my research scholars who are the pillars of this seminar. They are involved willingly, taken up their roles at the right time and working for the common good. In particular, I thank my research scholars Iniko Johnson, Omkar Ekante, and Ms. Sonam, who is really comparing this particular event. Once again, I thank Dr. Kaul, Professor Howe, and Professor Robinson for gracing this occasion with your august presence. And thanks for your nice words. We will deliver our best so that keep the spirit at the high. And thank you one and all present in this inaugural event. And thank you very much. And namaste. Have a good evening.
Thank you, Dr. Madhava, for recognizing the effort of all of us who are being present here today and who work day and night in advance to make this event possible. Again, I would like to thank our audience, and I hope all the registered participants have already received the schedule and would follow it diligently. I hope you gain some insightful knowledge by the end of this webinar series, and we expect this event to be a huge success by showing 100% participation. Try to make and gain the maximum out of it. Also, my sincere and special thanks to Dr. Robinson, Professor Howe, and Dr. Prachi Kaul for taking time and joining this inaugural event despite having busy schedule. I request all of you now to stay back for the presentation series, which we will be starting immediately. This is all from me. Thanks to all of you for being a great and patient listener. I will see you after this presentation round. Till then, enjoy your day. Signing off, your host for the day, Sonam.
So I can share mine. Yeah, thank you very much for registering for this particular event. And we are going to start immediately the lectures of the ATWM 2022. The first lecture will be really given by Professor Hu Hao No. This is how he taught me to spell his name. And he also told that like you can remember till the lifetime, like Hu Hao No. And thank you very much to make the pronunciation simpler. And Professor Howe is the distinguished professor in the School of Civil and Environmental Engineering at the University of Technology, Sydney, UTS. And he works in the area of wastewater treatment and reuse, environmental biotechnology and sustainable development. And also he worked in the area of membrane technology. And you can see the number of publications come out from his group as well as his leadership. Number of papers is greater than 650, and so far Professor Howe has the citation of close to 40,000 with a H index of 96, and he has holding 5 patents so far, and he conducted a number of projects in the research areas. And to make very briefly about his awards and achievements, he is the Deputy Director and also the Director for Center of Technology, Water and Wastewater at UTS, and Web of Science, highly cited researcher in 2 categories of environment and ecology and biology, and biochemistry in 2021, in category of biology and biochemistry in 2020, and category of crossfield in 2019, and Mendeley data top cited researcher in 2020. So according to research ranking of Australian, named as leader in environmental science and biotechnology 2021, leader in environmental science in 2020, and leader in biotechnology in 2019 in Australia. And Professor How is the editor of Bioresource Technology and also Chemical Engineering Journal, which are two of the top journals in environmental engineering. Most of the researchers want to publish in biological work into bioresource and most of the physical chemical work into chemical engineering process. And he is also associate editor in number of journals, top quality journals like Science of the Total Environment, Journal of Water Processing Engineering, and others. And more about Professor Howe can be found in his profile. I do not want to take a lot of time. I like to listen from Professor Howe, and more information can be found in this particular link here. With this very, very brief intro, I welcome Professor Hu Hao No to deliver his lecture. Thank you. Professor Howe, it's over to you.
Yeah. So can you see my slide?
Yes, Professor Howe.
All right. Okay. Thank you so much for such a nice introduction. And just save time, I just like to, the topic whatever I like to, to share with you today is the circular bioeconomy-based application of an aerobic membrane bioreactor for sustainable development. And just like my duties, every time before I make the presentation, I go very short introduction about my university, University of Technology, Sydney. And you can see that is very special when you come to the Sydney, and the UTS in the center of the city of Sydney, and very close to the, to the Opera House. And the UTS is a very young university. You can see established in 1988. So that means only 34 years old. And located in the CBD location. My university has more than 45,000 students, including 12,000 international students. And it's very interesting that we have more than 10,000 postgrad students. That means it includes that PhD and master student. Okay, so about the ranking, it's a very, that not too bad at all. For the US, according to the QS, UTS is ranked 137 and number 9 in Australia. For the time higher education, is ranked 133 and 9 in Australia, the same thing. And the first ranking in water resource, according to US News, and I forgot to put that is the second ranking for water and sanitation, according to the. All right. So about the university under 50 years old, UTS is ranked number 1 in Australia, according to US and the. And then the 11 in the world, and the 8th in the world is different. Of course, you get US 11, but the third is 8. All right. So now, after introduce at my university, now we go to the topic today. Firstly, I just go to the kind of give some idea about the background. When to talk about that is that seem to be whatever Dr. Cole mentioned about kind of the different challenges and especially in water. But is that basically at the time being, whatever we just talk about water, we talk about energy, and we talk about climate change. That is 3 major challenges we need to show. But we cannot forget the other thing as well, that is fertilizer, nutrients, fertilizer or something. This is related to our food is really important. All right. So now just have a look about the water problem. We just see the water scarcity. All right. So is that the first one? I just want to say 2/3 of the world population experience severe water, shortage. Okay, at least 1 month each year. And then is that go to the over 2 billion people live in water-strapped countries. Okay, and then we go to further, that is the, half of the world population could be living in area facing water scarcity by as early as 2025. It's really serious, actually. And then we should see some 700 million people could be displaced by intense water shortage by 2030. So all that is too much that we have to think about. And by 2040, 1 in 4 children worldwide will be living in areas of extremely high water stress. Okay, that is about the idea about the water shortage problem. Okay, now we come up with the energy. All right, so the energy is that come with that, definitely whenever we talk in energy, we will think about climate change and depleting fossil fuel resources. All right, so then you ask, according to the information we just see, the fossil fuel may be depleted in less than 100 years. So then what we have to do? So that's the reason we always think about renewable energy like wind energy, solar energy, or something like that. That is the way we are going. But honestly say, it's not that is the reason, or not that depletion of the fossil fuel problem. We have to think about climate change. Because because of the, kind of whatever, for example, from the coal, from, the gas, from the oils, whatever. I think when we go through the burning process, that means combustion one, you see, always we have the carbon dioxide, release the carbon dioxide to the air. And that is that we talk about the global warming problem. And then definitely, the final, the problem is that climate change. So we have to think about the clean energy. And that is the point is that we need to find some resolution. Okay, now fertilizer. Fertilizer is that after some time we will run out of the phosphorus or nutrient or something as for nitrogen or something like that. So I just show a very, the one figure to show you that about the fertilizer production. And what is the problem there? Eutrophication potential is there. The nutrient demand, that is because of the population. The population increase so high, and that is the food we need. And then, of course, we need to have sufficient nutrients. All right, but the problem comes because of something. For example, depletion of phosphorus rock. We are using that. We keep using that. But after some time, I think is that within 30 to 300 years, maybe we run out completely of the phosphorus. What should we do? Okay. And the nitrogen fixation as well, because we can get that the nitrogen from the air. Okay. But that is really disturb the nature nitrogen cycle. All right. So now the most hot topic these days, we talk about circular economy or something like that. And then what is that? It's that before we just, the people just want to earn the money. They just want to manufacture and then earn the money. But these days, we have to protect our environment. So that's the reason we have to go buy, yes, you can earn money. But at the same time, you have to recycle whatever you can. And then minimize as much as possible about the waste. Okay, so you can sit here, make, use, recycle. That is closed loop. And then you have some resource and you manufacturing, and then you are using, and then definitely, yes, something waste is here, but at least is that most of, if we try our best, more of that can recycling and reuse again. So the definition of the circular bioeconomy is here. I just write very clearly is that the virtuous cycle that we can amplify by influencing consumer trends and corporate emission. All right. So sustainability concept, where's that? That is whenever we use more renewable resource for energy, chemical, and material, something like that. And most important is that we keep using them in different, like the approach, for example, reuse, repurpose, recycle, upcycle of product, etc. Something like that, rather than we just throw them away. So this is a really, really important these days. Okay, so now when we talk like that, we just have a green technology or clean technology for sustainable development. And the purpose of this technology for what? Of course, it's that first resource, shortage, show the biowaste generation and the climate change or something like that. And then you see, I put here development of sustainable environment, and then potential renewable feedstock from what? From wastewater and solid bio-waste. Okay, and then from that feedstock, we can convert to become something like the value-added resources and bioenergy. So this is a really, when we know the concept, so develop some technology, we have a target. So that is really, the good way to do. Okay, so now we come to the circular bioeconomy. I just want to, I just say to you, it's just only economy, not bioeconomy. But now we could put a little bit further, actually just only BI, we put in front, BIO. And then a little bit different because the concept is kind of the sustainable scenario. That means it's conversion of the, like the bio waste to become biochemical and fuel, for example, bioethanol, biofertilizer, and then methane and hydrogen or something like that. And advantage is clear, very clear, because the anaerobic, the anaerobic process, they have a potential, high potential for biogas generation from different kind of the organic waste. So that kind of thing is the sustainable development. And the third one is that you just see, after you see like that, so then we come up like kind of the conclusion that this is the promising green technology in waste treatment, really. So that means anaerobic. These days we just talk about anaerobic for, green, for the green technologies. All right. So now, today, I just try to convince to all of you, anaerobic MBR is really the something for the circular bioeconomy. All right. So just have a look. Very simple. You just see. This is one reactor, anaerobic MBR reactor. Anaerobic MBR, just only an anaerobic bioreactor, and then we combine with the membrane. That is very simple. All right. But the good thing is that during the process, we can recover, the nutrient. Okay. And then whatever biogas, whatever we collect here, from the beginning, we can select whatever we want to have, like the volatile fatty acids, or go to the clean energy, is a biohydrogen, or we go to the final, product such as, like the methane or something like that. So it's excellent. In somehow we can. And then after we treat that, the effluent can be direct use for irrigation. And then we just say is that crop irrigation. Sludge, yeah, we come with that, whatever. The waste treatment, definitely we have some sludge. But think about it, the sludge from the anaerobic MBR, if we know we go to the anaerobic digestion, again, we can get the biogas, like the methane, all right, or even get hydrogen, clean energy. All right, so now we talk about biogas first. Biogas, methane, and hydrogen gas biogas. Everyone is that whenever we work for, like an aerobic that, like the pathway, we all know, they normally, they have to go to the 4th stage to convert the complex organic matter to become methane. All right, like hydrolysis, convert the complex organic to become solute organic molecules. And then the acidogenesis convert the solute organic molecule to become volatile fatty acid. That is very, very, like, if we just only want to produce the VFA, we have to stop here. All right, we not go further. That is the way we do. Okay, if we go further, so that means we like to have some of the other products, such as hydrogen, because like that these days, hydrogen is clean energy. And actually, is that our group is that focus on hydrogen production. So we will stop here. So that means we stop at acidogenesis phase. We not go to the methanogenesis. So we stop here. Okay. But if we go further, so this here you can see is a methane, and that's a conventional. Like the biogas production is a methane. That is nothing new to say about. Okay, so that is that volatile fatty acid, hydrogen, and then methane, whichever you can select, whichever you can control by the operating conditions. All right, so the biogas, like I just say about, in general, methane, about up to 75%, carbon dioxide up to 50%, and the molecule is there, and some trace amounts of other gases like nitrogen, smaller than 7%, or hydrogen sulfur, smaller than 1%, ammonia, smaller than 1%. But why I just show like that? Because biogas is, some, especially students, they confuse the biogas and hydrogen. So they make the hydrogen inside with the biogas. No, completely different. So just that hydrogen is not biogas, remember. All right, so now just see, based on the theoretical aspect, normally we can convert up to 98% of the influent COD into biogas by an aerobic MBR. Okay, so this is that, almost equivalent to 7 times of the energy required for system operation. But unfortunately, it's not like that. The real condition, because of, methane is that dissolved in the effluent soil a lot. Almost half. That is the thing. Okay, and then a lot of inhibitor, to stop the production of the methane as well. So that's the reason when we come up that with the actual biogas yield is much, much lower than, theoretical value. That is unfortunately. And then what we should do here, I just show, is a membrane separation process for methane recovery. So that means we use the membrane separation, and then we can collect the biogas as the methane, and then again we can do this kind of thing. Yeah, of course we can, but it's when we consider the net profit. We can do like that, but net profit is negative. That is, about it, the issue. This is critical issue. Okay, so now is that the biogas can be used like the fuel for cooking and for heat engine, for power motor vehicle, or this kind of thing. It's just that, it seems to be, most of people know about it. So I don't want to spend, much time for that. And one, just only the renewable fuel acting as the renewable energy subsidized in some part of the world, because that is the way they try. Okay, so this is very interesting. Just show you the case study. That is that when we use an aerobic MBR for the biogas production towards energy generation. Okay, This is that, I mean, in somehow for this one is the distillery waste treatment by Veolia, I mean, in Scotland. And then you can see from the, I mean, from the pot owl and the wastewater span lead, whatever, go to the inanimate MBR here. They can produce, that means from the 12 tons COD per day, they can produce 5,500 cubic meter per day biogas, and then can produce at 1,600 kilowatt per day. So it's so nice. Some highlight is there also because after that, the effluent we can discharge to the water course without any problem. So that is one very good, case study about anaerobic MBR. Okay, so now we go to, in Japan, they love to drink, soju, something like that. And they have a lot of soju, the plant, the manufacturing plant. So this is the thing when they think, why not they use an anaerobic MBR? Yes, they use in some, for example, like the anaerobic bioreactor with the, the thermophilic and mesophilic, condition at the digester. And then they connect with the MBR, okay? And then they found, it's a good thing, when they found, they can have the biogas for the power generating facility, okay? So like for the boiler, especially, like something like that. And then the wastewater treatment is quite nice because when go through the membrane, so the quality, exactly like the previous one, I just showed you the, like the case study, they can discharge, to the water course. All right. So until 2010, they already have 15 full-scale plants in Japan. And I think it's now with the 2022, I believe that they can have more plants, whatever, because that is the, the successful, treatment. So they will follow if they have a new plants, like in Japan. All right. So another case study I just want to show you is that how good an anaerobic is. For example, UASB and membrane, that is one kind of an anaerobic MBR. And they can produce, up to 0.42 cubic meter methane per square meter day. And then is that to treat the domestic water, when we have expanded granular sludge bed, and then they go up to 0.58 cubic meter methane per cubic meter day. All right. So then you can just see, for example, municipal wastewater, we go for an anaerobic fluidized bed reactor and membrane with that. So we have an anaerobic MBR, and then they can produce 4.11 mole methane per square meter. And for one, example about the synthetic wastewater, of course, is this one I just want to show because we can use even dynamic membrane bioreactor. So dynamic membrane where the bioreactor is not really rely on the membrane. We rely on some of the other things, but when they build up with, like the substances build up and then become the membrane itself to filter the water. Okay. And that is again, it's domestic wastewater. And we have a very, interesting, is later on I will talk to you about, that is almost the osmotic membrane bioreactor. These days is very, really nice, anaerobic osmotic membrane bioreactors, and for osmotic wastewater. And then is that why I keep saying municipal, or domestic wastewater or something, because the organic matter is very low in the wastewater, but we still can produce, nicely the hydrogen, the clean energy from from the wastewater, because we know how to condense them, how to, to get that from the bioenergy from biomass. Okay, so now about the hydrogen, because when we talk about, we really think about is that how we can have a biohydrogen. But this is really the circular economy and sustainable development. This is the one, like to let all of you to have a look at that. When we have a bio waste, we need to see we go to the recycling. And then normally we use dark or photo fermentation, or we use microbial electrolysis cell, to produce the hydrogen. And when we have a biohydrogen, we will support for the air, for the heat transportation, electricity, something like that. And then again, we have a biowaste production. And then we go, it's like closed loop again and again and again. But this is very nice when the people see circular economy, sustainable development. All right. So the people just say, why you need to produce the hydrogen? What is methane is that is so, like the tradition. And then we just care about the methane. Why we care about hydrogen? No, it's completely different. Methane, like to have some, like carbon dioxide and create climate change. But for the hydrogen, fully you can see hydrogen and oxygen atom move towards to each other. They combine, releasing light and heat. And then a water molecule is formed. So it's nothing, that can make that, our environmental become the problem with the global warming. Okay, nothing like that. So the people say zero and near zero emission. Zero or near zero emission. In fact, we can say a practical zero emission. Okay, practical zero emission. Okay, so now, this is all right. I think is that for biohydrogen, the use of biohydrogen is normally hydrogen vehicles, synthetic fuels, upgrading oil or biomass, ammonia fertilizer, metal refining, heating, power generation for electric grid infrastructure. That is just on the summary for about the use of biohydrogen. But now, actually, because I like to convince to you about an anaerobic MBR can make good, can produce efficient, high efficient of the volatile fatty acids and hydrogen. Okay, so it's very simple. We just use the single state submerged anaerobic MBR. So that means we place the membrane inside the anaerobic bioreactor. Okay. And then you can see we have we have a pump, and then we have we use the synthetic wastewater. We have a biogas analyzer to, we can analyze the VFA and hydrogen or something like that. And then normally we take the sample from, inside the anaerobic, that's the slot go to the, to the top part and the biogas. But anyway, the nitrogen we need to purge in light. So that means we keep that anaerobic condition. All right. So about the membrane, we use that PVDF, the hollow fiber membrane, and the pore size about 0.1 micrometer, and working volume just very small. We use about 3.5 liter. Okay. So now that is whichever, I think I go very far to the VFA because that the attraction, go through the step 1, acidification, centrifuging, and then we go the filtration, solvent attraction, and then dehydration, centrifuging, attraction of the organic phase, and then the step 4, dehydration, and then filtration, and then we can quantification. All right. So now, what I just want to tell you about that is about the production of the volatile fatty acid at different hydraulic retention time. Because in fact, from the hydraulic retention time, we can control well to produce which product we want to, VFA or hydrogen or like methane. So that I mentioned to you before. And this becomes very, important, but for the optimum HRT is 8 hours. Whatever, from here we can see the acidic, that is that we can get up to, like something is that 1.2, around 1.2 millimole per liter or something like that. Of course, that different kind of the volatile fatty acid, like the acetic acid, propionic, or like the isopiteric or piteric, etc., or something like that. Of course, the acetic acid is the highest one. So I just mentioned that here, on the top of the figure. Okay, so different organic loading rate as well, because this is, we see, for example, the with the COD with different, like the organic concentration from 550 to 750, like the milligram per liter, in something like that. And the highest yield can go up to 48.2 milligram VFA per 100 milligram COD feed, or we say removed. And then is that for the pH, very interesting. This is really interesting because we vary with different pH value. And you can see is that pH is 5. We have a 62% acetic acid. So that's the reason we can use the pH, like the value as the, like the control parameter to produce the acetic acids. It being pH at 5, 62% acetic acids. pH 6, all right, 61. So pH 7 is 66. So that means 5 to 7, we can, we are okay to produce the good acetic acid. But if we want to think in something else, though, then we have to go as higher pH, for example, go up to 12. So then at that time is that on is the isopiteric acids, as the the dominant. Okay, so the VFA drop at the alkaline pH condition. So that means we don't want to see, further, like the higher, after the 7, they keep dropping, especially acetic acid, the pH 10, you just only see the 52% acetic acid. Okay, so now about the biohydrogen. Biohydrogen, you can just see whatever at 6 hours, you can see at 6 hours, you can see the hydrogen yield is at the highest. And of course, it's that the people say, when you control the HRT at 6 hours, how can you have a methanogenic material? No way. So that the reason is that they're not going to have any methane. And then everything will focus on the hydrogen. So that's the reason. But when we go to 24, 24 hour, oh dear, it's on that very low. Why? Because the competition between the, methane, zonic, methane, zenic material and the hydrogen one. Okay. Then we just see the optimum pH is that 5. That means that we can get up to 122 milliliter hydrogen per liter day. So this is again interesting. Is that 5 is so good. Even that when we say about the VFA 5 to 7, but for the hydrogen is 5, it seems to be the best. But of course, is that they close to each other for 6 and 5, but is significant worse in the neutral condition. So that means pH 7. All right. So the optimum pH 5, we have a higher yield as well, 65.38 milliliter hydrogen per gram COD. Exactly the same is here. Okay. So now we are happy to show about the biohydrogen production rate and yield from different study. The different study, they use multi-phase and aerobic reactor, two-stage and aerobic fermenter, Okay, two-stage anaerobic fermenter and a lot of things like plus with that PAC or two-stage UASB, whatever. But we are very simple single-stage anaerobic MBR only. We already have a specific hydrogen production rate up to 122.21. Compared to the other, it's really, really matter because the people spend a lot of money for the other because they go for the multi-phases and then is that in somehow. And for hydrogen yield as well, you can see it's comparable. It's really comparable because we use conventional single-stage anaerobic MBR. Okay. So for sludge, that is a very, simple. I just go. It's that because that from the methane recovery from sludge by anaerobic digestion process. So most of the people know anaerobic digester, they will produce that the methane. And then you can see this is the final products, methane. Okay. And then these are from hydrogen, but from acetic, yes, they have a carbon dioxide as well. And then that's about the nitrogen and phosphorus recovery. Normally we can recover by different, technologies, like through the subsequent precipitation at fertilizer when we have the ammonia, magnesium phosphate. So then we can have a stratified at the fertilizer. And then we can have kind of the direct irrigation for crops as well. All right. So this is that very simple. The idea to have either, the nutrient recovery as the stratified, or we use directly, from the effluent for the crop irrigation. Now, this is very interesting, what I just mentioned before. We go for the osmotic membrane bioreactor, the anaerobic membrane bioreactor. And this is that the way we design special rotating, the osmosis that the module. And then is that we can increase the water flush, and also we can reduce the fouling. Yes, so this is really nice. And osmotic forward osmosis, the forward osmosis and reverse osmosis is different. And here we use forward osmosis. So we don't need to have to give a lot of pressure. Just only we rely on osmotic pressure. From the low concentration, they will flow through the membrane to the high concentration. So that's the reason we have raw solution here. Okay. And then after we keep condense, the enrich, we say is enrichment of the phosphorus and nitrogen, then we just use the MF. They let them to go to the MF. We collect here, okay, magnesium, phosphate, and then ammonia, and then we can have the stratified for fertilizer, okay, use it and use as fertilizer for agriculture. But this system, why we just say, when we combine them, we have to think how to integrate them to do, the job at one time. And you can see it's really matter. We just use that. You can see after this one, we go to, for example, membrane distillation. Then we can have a clean water for reuse. And in fact, this one normally we can drink up to that kind of quality. It's very high quality. And this is that the result from our research is that high removal of ammonia and phosphorus by the whole system, more than 95%. High rejection of ammonia and phosphorus by the forward osmosis membrane. Okay, so this is that about our work. I just show, two work. And then heat energy, very simple, because methane released from anaerobic, we can go to the heat energy, the enthalpy from methane with oxygen, then we have carbon dioxide and the water. But it's normally we can use for commercial, residential, and then institutional and government. All right. So now, conclusion and future perspective. I talk a lot. I just try to different way to convince something. But this is the conclusion. An Arabic MBR effectively produce a significant range of products from bio-waste. Before, the people never think that way. The people just only use an Arabic digester to treat the sludge, and then they can have a methane, the biogas, something, or some the other bioreactor, but it's not an Arabic MBR. But with that kind of trial, you can see, yes, our trial is a very, different with the other, but we're very happy to tell all of you about that, and you can try yourself. And then is that ensure sustainability of the environment and potential for financial gain. So that is the thing, because when you can treat the wastewater, we can get the bioenergy from the wastewater. We can recover nutrients from the wastewater. It's so good. So that's the reason we can say we ensure the role of an Arabic MBR in the circular bioeconomy. But one thing, whichever, I just showed you that only the bench scale. Who believe that, bench scale to go up to the full scale is no way. So that's the reason I think is that I really like to encourage the people to go for, to pilot scale and then go further for full scale application or something like that. Then, we have we can really to have a kind of the circular bioeconomy application. All right. So that is that the very important is that to produce biohydrogen or volatile fatty acids instead of methane towards zero greenhouse gas emission. That is really important. And you know, is that this day, the whole world, it's not in India or Australia or something, it's the whole world. They say net zero emission. Okay, so acknowledgement that I just would like to thank to our team, MBR team, that Professor Kuo and Dr. Dang, and also we have some, the collaboration with that Joint Research Center for Protecting Infrastructure Technology in Environmental Green Bioprocess. This is the MBR research team member. And then, of course, is that with the IIT Madras, with the Professor Kumar and Mata Kumar, we have a very, very good collaboration on the algae photobioreactor membrane, an Arabic membrane bioreactor. So this is that we keep doing, and I think is that we will develop some novel, technology. Okay, so thank you so much for your attention. And then is that I don't know how to say, have a happy day or something like that. But of course, I just say have a happy day and take care because it's a different time. So I just say like that. We cannot say night or day or something. All right. Thank you. Thank you so much again for your attention. And if you have any question, please just let me know and I will try my best to answer.
Yeah, Professor Howe, thank you very much for the very detailed lecture and insightful into the anaerobic MBR and the key details of how to operate and construct in the perspective of sustainability and circular economy through anaerobic MBR. I request the participants, if you have any queries, there is a Q&A chat where you can really type in your question so that we can convey to Professor Howe to answer. The similar way we'll engage for the all other speakers as well. I think somebody raised the hand, but I request the participants to really type your Q&A so that we can convey to the speaker and get answer. And I see Professor Lim here. Would you like to speak a few words if you're available?
Thank you for calling me. I think it's very impressive presentation. It contains a lot of materials for us to digest. I think that is a good first talk to inspire us how to prepare a presentation. I don't have the specific question to ask because I'm not working in this field. Okay, I'm more in the physical chemical processes, and I have a presentation on Monday. Also start at 6 o'clock, I think, or 6:30. I hope that I also have a sizable audience for my talk. Thank you and good night.
Thank you. Thank you. Thank you.
Thank you. Yeah, Professor Vincent is here, so you wanted to give some feedback about the lecture, or if you have some questions, you can.
I think it's a very excellent presentation. I don't have more questions. Just let the floor ask questions.
Yeah, thank you very much. I received a question from one of the audience. Shubham,
I think in the chat, how to reduce fouling in anaerobic MBR.
Also membrane operation is energy intensive process.
Yeah.
Professor, how?
Yeah. So about the membrane fouling, right? It's normally the anaerobic MBR is that the membrane is quite serious actually. Is compared to the aerobic MBR. Yes, but the thing is, when we know, I mean, the reason when we just try to produce the clean, clean hydrogen or volatile fatty acids, and from that, I mean, I forgot to put that the TMP to show today about the membrane, and we found the membrane fouling is much less than, for the methane production. First, the second, we develop, successfully, it one kind of the, the material with the name is gem flux. And that is that whenever we just one day, we just add one time the gem flux in, and the membrane fouling is almost is that to the, to the practical zero membrane fouling for a long time. Maybe it's go up to, the more than 3 months. And then the TMB is keep, constantly, it's not more than 30 kPa. So that is the one I just say. We can apply that material for an aerobic MBR. But by the way, I just suggest the people to do the simple way. It's relaxation. Okay. So that means that just only 1 hour, just leave for five minutes for the relaxation or something like that. And then to just, kind of combine with the, in some way with the chemical, like the, what is that, cleaning or something that is all right. Or you can combine the physical, like the cleaning together with the, what is that, the chemical cleaning or relaxation. But I think relaxation is quite good because we try that, relaxation and physical cleaning. Chemical after some time, definitely. But with the gem flux, we don't need to. Okay, so that is my answer about the membrane fouling. About the second one is about the energy, right? You just asked the second question about what is that? What is the
membrane process are energy intensive? So how to really do a solution for it? Membrane process in
so energy intensive.
Yeah.
Energy intensive.
Yeah.
At the moment, at the time being, or you mean that because that's the energy intensity, what that I just keep trying to say, the people will think about the hydrogen production, and that is the future we can see. I mean, that is the future for the bioenergy intensive. And I'm not at the moment, if I just say one is that is a very, very certain about that is not the good. We have to go further. And then after some time, I think is that, because in my opinion is that I really like hydrogen compared to, the methane. And that is the reason is that I just try to persuade the people, convince the people not to go for methane because of, the benefit, positive, financial gain is not just like the methane. We have a negative, final net profit, something like that. And a climate change or global warming problem, etc. All right. So that is the thing I would like to say. Okay.
Professor Howe, we will take 2 more questions. Due to time limitation, we'll take only 2 more questions. Other questions we'll consolidate and send it to Professor Howe and get the clarification. Right.
No
Please
problem.
bear with those. The first question is from Vinay Tripathi. If wastewater is thermally treated before anaerobic MBR operation, will it enhance the overall efficiency or it is detrimental to membrane life and the microbial activity?
Can you tell me again? I'm not clear in that the first sentence.
If wastewater is thermally treated before anaerobic MBR, will it enhance the overall efficiency or it is detrimental to membrane life and the microbial activity?
My answer is definitely. The only thing is that because today I don't talk about the hybrid system. So that means an anaerobic MBR, in fact, the need is either the pre-treatment or post-treatment. All right. So that is the thing, definitely is that will affect the, the efficiency, the bioenergy production efficiency, and also, the membrane fouling as well. It's really important. Okay. So if you use, for example, I just say it's 1 stage, but when the hybrid system comes, so the burden of membrane fouling is much less, much less. Okay. So I think that is that, the good way, think about hybrid system, because I just say is that today I'm only say single stage, but is that the actual system have to be hybrid system for an anaerobic MBR. Okay. Yeah. And one
last question.
Yes.
Can you explain more about GemFlock?
Oh, GemFlock. Yes.
How really make whether it is implementable or not in large scale?
Yeah. That is the thing. That this is the nature. This is nature. Material, whatever. It's not chemical at all. Okay. And then is that the second thing is that we go for the charge. That means is that the thing is that whatever we make that to add in 2 things. First, they repulsive force. So whatever they protect the membrane with the other, for example, polysaccharide or protein, whatever, when they come to the, the membrane surface. So then the GemFlock can help to, to push them away. That is the first good of the GemFlock. And the second good is the GemFlock is the fully, the biodegradable. So that means they become the food. They become the food for bacteria also. So that means they enhance, bacterial, activity. So that means, for example, they only eat 2 kilograms per day, for example, organic matter per day. With that GemFlock, they can eat 3 kilograms COD per day, for example. So this is the way when we think of that is the international patent. I think is that about a few years ago. So this is this type of thing is the 3rd generation, and now we are developed in the 2nd and 3rd generation. for that. And then is that this is the fundamental concept. Of course, we cannot go further because confidential, but that is the concept, the idea. That means to push away what we just say is some pollutant or something to stick on the membrane, or have got no chance to go inside the pores of the membrane. So how can they have the membrane falling in this situation, right? That is a very simple to understand. And then biodegradable is not non-biodegradable. So they cannot create anything for the secondary pollution or something like that. And the third good thing, I forgot to tell you that when you add in, that means very less amount of the, of the gem flock. And the second thing is that only once per day. So whenever, for example, 30 tons per day of the, fluoride or something, or flush, for example, we only add 1 kilogram 1 time per day. So this is very convenient, very, very convenient. So this is the one we are, of course, it's now we keep trying with the pilot scale. That is that testing successfully, and now we try it in 30 cubic meter per day. So that is kind of the big, it's quite a large pilot scale at the time being. Okay, so that is my question, my answer.
Yeah.
Yes. Yeah.
Thank you very much, Professor Howe. And
yeah,
I think it's time. Just crossed an hour, so we have one more lecture session by me. And thank you very much for the questions from Nagaran, Gabriella, and Sudalai. We will get back to you respond to the speaker later. Yeah.
No problem at all. No problem at all. Thank you.
Yeah, thank you very much, Professor Howe. Very interesting, very eye-opening, and tips for the researchers to really construct and operate the anaerobic MBS in the coming days, probably lab scale as well as scale up for the future. That's the key, which is really needed.
Yes,
and Thank you very much.
Okay.
Thank you.
Thank you. Thank you. Thank you so much. Okay. Thank you.
And good night.
Thank you and good night.
Professor Lim and Professor Venchan, thank you very much too. Yeah. Thank you very much. See you.
It's quite late. Yeah.
Yeah. See you.
I think I will leave after this session. Yes.
Yeah. Thank you. Thank you, Professor Howe.
Yeah. I just like to stop that. Yeah. Thank you.
Yeah. Thank you very much.
Yeah. Thank you. Yeah.
Yeah, we will move to the next lecture. I have to give my lecture for about an hour. And I request the registered participants to type your question if you have in the Q&A, so that we can answer few in live, and we can also able to answer you later. Probably we'll get you back with the answer in the coming sessions. Right, so we will just go back to the presentation of mine. Yeah, so we work on water purification as well as wastewater treatment at IIT Madras. And I thought I can give you an overview of how the wastewater management is really done and what is the need for advanced wastewater management. And I just wanted to give you some glimpse about when we can really apply the membranes, advanced oxidation, and algal photobioreactors. Right. So I'm just going to give only the brief overview of this with respect to wastewater management in a domestic wastewater treatment plant. And in the coming lectures, you can get the details about if somebody wants to prepare a new membrane, or maybe a coupling of new materials with advanced oxidation. There are speakers really lined up even for the algal photobioreactor and energy out of algal photobioreactor in the coming days. Then moving on to the introduction, we all know about the sources of water, even the school our kids are really started to know about more sources of water. Right. So I added, out of curiosity, the wastewater is a constant source for water, and if we properly treat the wastewater, this can also be given as an input to manage our daily water demands. Right. So proper treatment is really lagging, and people are really relied on advanced systems to treat and really meet the expected level of disposal and reusable standards. And we also look for water from the air by really harvesting the humidity which is really present in the air. And as per the standards, like TDS less than 1000 milligram per liter is termed as fresh water. Even many people do not have the right water which is having the TDS level of less than 1000 milligram per liter. And the water which is really available in the purest form is also less, and day by day the pollution is also increasing. Obviously, we have to treat it to the purest quality before we discharge. And this is the water demand in different sectors in India in billion metric cubes per year. The demand in 2025 is really 1093 billion metric cube, whereas it really increases to 1447 by year 2050. This is as per the data from the Jal Jeevan Mission report. And the per capita water availability in India, you can see that as per the last year's data, it is 1,486 cubic meter, which is really available. But this will really reduce because of more population increase and urbanization. But current rate of supply are really, for urban, we supply at the rate of 135, and the rural, we supply only 55 LPCD on a given condition. And coming to the estimated proportion of household wastewater safely treated in different countries, this is as per the Sustainable Development Goals report released by UN, the 2020. So you can see here, I take the context of India, the household wastewater safely treated in India is only like 26 to 50%. I'll also give you the data for it. But if you take only like 26 to 50, meaning that the rest of the water is really discharged without any proper treatment. And India is really categorized in the report in the Central and Southeast Asia. And as per the SDG 6, clean water and sanitation data, the household wastewater volume generated in this particular region, Central and Southeast Asia, is 52,450 million metric cube per year. But the data highlighted in red is corresponding to Indian data. India is really releasing 34,532 million metric cube per year. And the domestic wastewater generated in this particular regions are around 70 liters per capita per day. And the domestic wastewater safely treated in this region is 25.5%. And India treatment efficiency is only 26.6%. So this is the worth report to really study and understand how much the volume generated and how it is really treated and how it is really treated in different units. Usually, like we call it as treatment plants and on-site soak pits, and also it is treated differently for industrial wastewater. These are all the three categories which is really distinguished in the particular SDG report of UN. And now, why wastewater management is really critical? This is the 2022 report as per the United Nations overall sustainable goal. You can see here for at least like 3 million people, the quality of the water that depend on is really unknown because lack of monitoring data. And this particular graph you can see here, this is the basic drinking water. That's the first graph. The data is like around 90% of the people has the basic drinking water access, but safely managed drinking water, only 74% of the people only knows. So to achieve this target in 2030, if you progress in the same rate, it may not be possible. So you accelerate our treatment techniques and data monitoring system so that we can do it at a large phase. Then in the defecation side, right? So no open defecation and basic sanitation, right? So open defecation is really no open defecation is 94%, and to make 100%, that's the goal in 2030. And the basic sanitation facility, usually like only 78% of the people have as per the 2020 statistics. and safely manages sanitation only 54. So this report clearly says that our infrastructure towards wastewater management and waste handling supposed to be increased at a much higher rate than at present, so that we can meet these set goals at 2030. And this is the overall map, which is really showing the global water scarcity in 2025. If you see here, there are two types of water scarcity. One is physical and another one is economic water scarcity. The physical water scarcity is water is really available not in the purest form. And the economic water scarcity is the water available not at the purest state. So obviously we need some funding to really treat the pollutants from your wastewater. So we all know that the historical events in water supply wastewater treatment is not really new. 4000 BC, people were started treating the wastewater, and the sequence goes. And 1902 AD, the first drinking water supply was done with ferrochar. Even the ozonation was done at 1906, and safe drinking water passage was really done at 1974. And if you see, the challenge towards this 21st century is reduce the exposure of man-made chemicals and microbial contaminations. That's the key, and people are really working on this at different levels. And the risk assessment methodologies to assess the health risk is the next important thing, other than reducing the exposure to man-made pollutants. And the sources of water pollution, if you see, there are point sources, there are non-point sources, and there are transboundary sources, because the water resources are really shared between the countries. One country started to pollute, probably the other country may really receive the pollutants. So obviously, the cross-border contamination is also possibly a key. So when you really design a wastewater treatment system or water purification system, we definitely need to understand what is the chemical characteristics as well as the biological characteristics of the pollutant which is really present in your aqueous systems. For sometimes, industrial pollutant may be really different from an agricultural runoff or maybe like a storm runoff. So obviously, you need to distinguish and you need to make a thorough analysis of the water quality. So if you see the water contaminants, usually you have the physical, chemical, and biological contaminants, but you can also classify them into different categories: suspended and dissolved, volatile and inert or fixed, organic and inorganic, biodegradable, non-biodegradable, reactive, non-reactive, toxic, and non-toxic. So if you classify them into different categories, these are all the example of the pollutants like pesticide, emerging pollutant like pharmaceuticals, halogens, and the personal care products, and you have a lot of heavy metals, synthetic dyes, halogen. If you classify all these things into different categories, you can really able to design what kind of treatment technology you want. For example, like if I wanted to remove the suspended matter, I do not want to go for an RO membrane. For example, like my dissolved solids is really much bigger, then obviously do not want to go for a RO membrane level, but I can really stop at the level of ultrafiltration or microfiltration membranes. Similar thing, if a pollutant is really biodegradable, for example, you want to express the organic compound in the form of BOD or COD, if they are really biodegradable, obviously a setup like anaerobic MBR will really fetch you the biogas generation potential, like CH4 or hydrogen gas or any other acid which you can really produce by stopping the reaction at various levels. Whereas if the pollutant is really toxic, right? So obviously I cannot really rely on the biodegradable mechanism because the toxic nature is there for the microorganism. I need to identify a different process other than a biological method. That time, it may be possible to adopt an advanced oxidation process first. Probably later on, once the toxicity is reduced, you can really go for any biological process, including the algal treatment. So systematically, you can identify and understand what kind of pollutant, classify them, then really couple the process in a lineup. And if you see the water contaminants, right, there are different common water contaminants. starting from organic matter of different varieties. You have a nitrogen in the form of nitrate as well as phosphorus. Then you have a metals and other nutrients, maybe like a calcium, magnesium, and other. And you have a dissolved ions. And most recently, people are talking about the emerging pollutants and also microplastics. So if you wanted to, because we as a group work on emerging contaminants removal, there are a different variety of emerging contaminants like pharmaceutical, as I already said, personal care products, pesticide, industrial additives, surfactants, and flame retardants. So now you have Indian standards, right? So these are all the different Indian standards that we have, and each one of the standards express the allowed limit of pollutants which can be present in your waste stream, right? But for some of the emerging compounds, we don't have the limit in the disposal standards. When you really wanted to treat a source or aqueous solution with different treatment techniques, usually like our domestic wastewater treatment really line up in this format, primary, secondary, and tertiary treatments. And I would say that we are really very effective till the stage of secondary treatment. And the process has to really emerge for doing the tertiary treatment as a whole. But why the need of tertiary treatment? If you really rearrange your wastewater treatment schematic diagram in this particular format, you can see here, starting from screening as your primary treatment, you will go for a sedimentation, biological treatment if toxicity is not there. If toxicity is there, we replace it with some other compound. Then you have the nitrogen and phosphorus removal. You have a trace organic removal, disinfection, and reuse. This is a detailed 8-stage process, but usually we stop at the level of step 4 and we directly jump to disinfection and we really send it for disposal. But if you really wanted to reuse, the pollutant like emerging contaminants, nitrate and phosphate and trace organic matter supposed to be removed. And we also face the problem of disinfection byproducts, DOPs. By means of chlorination, we really form the chlorination disinfection byproducts. If it is a ozone-based disinfection byproducts are really formed. So obviously, we need to take care of this disinfection byproduct, which is really formed when trace levels of compounds are really present here. Now, if you line up your tertiary treatment of your wastewater, right, you have the combination of treatment process. For example, like coagulation, flocculation combined with sedimentation and filtration, or you have a carbon adsorption, advanced oxidation, and membrane filtration. These are all the sequence, but you can really rearrange the sequence based on the type of treatment which is really required to set your reuse goals. Now, as I said, like this emerging contaminants removal, mainly done by these three, are combined with all this in addition to other processes, including the algal technology. But if you open and see a small water filter that we really use in our household, exactly it will really follow the format of your tertiary treatment of your wastewater. So you have a sediment filter, and before that you have a pre-filter, which is removing the solids of several tens or hundreds of micrometer. Later, the wastewater is passed through a sediment filter, and it is passed through a carbon filter to really remove sorbable organic compounds and other materials. Then it passed through a UV unit where coarser dissolved solids are really removed here. Then ultraviolet disinfection will really degrade the microbial substances, but it will really lead to the disintegration fragments. So that fragments will be really retained by your nanofiltration membrane or maybe like a RO membrane. So obviously there is a way to really combine and couple all these processes based on your requirement. Now, this particular lecture, I'm really going to give you some examples of how really we do in membrane modification in the context of water purification as well as the wastewater treatment. We will move on to one classic example for advanced oxidation process related with photocatalysis. Then we also move on to finally an algal technology, how we can really combine when you have advanced oxidation upfront. This is the whole idea. So membrane technology, if you ask me why membrane technology, we wanted to remove suspended as well as dissolved solids based on membrane permeability and molecular weight cutoff from aqueous solution. And we also really selectively remove pollutants, and non-selectively also will remove pollutants. So we prepare membranes for both these goals. And if you ask me what research we need to conduct on membrane technology or why to improve the membranes, so the membranes are really improved to decrease the surface roughness, so that we heard about the term fouling. So obviously we wanted to reduce the fouling in such a way that the membrane will be performing its role for a very longer period of time, so that like we can save energy input which is really given for membrane operation. Then item number 2, improve both water flux. That means the quantity of water which can be really passed through a particular membrane in a given time with a given square meter area of the membrane supposed to be high. So obviously we will work for improving the membrane, increase the water flux, and we also improve the membrane for rejection rate of any pollutants. So for example, like we want to target TDS, which is expressed as NaCl, so we wanted to really remove it. So for example, we wanted to remove nitrate or phosphate, we wanted to improve the rejection rate of nitrate and phosphate. And if you really operate for a longer time and you wanted to really, the membrane is really foul, for example, so you wanted to clean them using some solution, right? So for example, like chlorine solution, right? Usually we use light chlorine solution to really oxidize the organic matter which is really present in our some dilute acids to really remove the foulants which is really accumulated on the surface. So if you really apply this chlorine solution or maybe like an acid, it can really disintegrate your membrane surface. So we improve the surface in such a way that the stability of the membrane will be there for a very longer period of time. And before going into membrane, I usually keep this particular slide to talk about what sequence the membrane filtration operation is really done here. So if you can look at the right-hand side, you have the conventional filtration, which is really for the removal of much bigger particle like bacteria, algae, and sand. But if you arrange the membrane technology, it is also work like a pore, right? How much smaller the pore, that will determine the name of the membrane. So the bigger pore membrane is a microfiltration, followed by ultra smaller, and the smallest being nanofiltration, and the much smaller being the reverse osmosis. So if you apply the reverse osmosis membrane, you can able to remove metal ions, dissolved solids, pesticide, and sugar. But you really do not want to load the reverse osmosis membrane with all the pollutants. So obviously you use a combination by means of doing UF followed by NF or MF followed by UF, or the combination of MF, UF, then your RO, so that like you can distribute the loading of pollutant into membrane in a sequential fashion. So that's how your water purification units also really arranged here. Conventionally, you have two different classes of membrane. One is a flat sheet, right? It's something like a representation of a A4 sheet. So it is really mounted in some mounting arrangement. I'll show you later how it is. And you also have the hollow fiber modules. For example, like you have a straw. So similar to that configuration, there are hollow fiber membrane modules, which is really assembled. There are two varieties, but mostly in our research group, we work on flat sheet membrane modules to really operate it, because most of the customized RO modules in your commercial applications, both wastewater treatment and water treatment, we use flat sheet, which is really rolled and brought to a circular cylindrical format. Right. So why we have to identify the pollutant? This particular slide give you an idea. So I put from membrane, microfiltration membrane to RO. If you wanted to increase your energy, right? So the energy consumed will be very large in an RO membrane, whereas it is less for MF. So if a pollutant nature can be removed by MF, if you operate with RO, then energy required is really 25 times higher in terms of kilowatt per hour meter cube of water treated. And if you really wanted to flux, if you really compare, your membrane modules can really produce 4 times higher flux compared to your RO membrane module. So need-based membrane module arrangement is really required if you wanted to adopt a membrane technology in the field. So for that, you need to really understand what kind of pollutants are really present and what kind of membrane will be really sufficient to really remove these pollutant structures. And the best thing of membrane technology is even for your small research work purpose, so you can prepare a membrane of as small as like this. And in IIT Madras, the zero liquid discharge laboratory, we have the facility for preparing small scale flat sheet membrane modules. And we also have the testing kit for testing to find out like how the fouling is really occurring, what is the flux, and what would be the effect of temperature, what would be the effect of conductivity on these membranes. We can able to really find out, and the membrane test kit can go up to 69 bars with temperature controlled chiller arrangement. And now we wanted to modify the membrane surface, right? So as I said before, if the pollutant is really passed through a membrane, so obviously they try to accumulate on the membrane surface. We do not want to accumulate the pollutant on the membrane surface. So we incorporate some kind of a material on the surface in such a way that the fouling will be delayed, or fouling should not really happen. So for that purpose, we really coat different materials on the membrane surface. So our group, we really work on a surface modification using nanoparticles. There are other technologies which is really available, like photoredox initiated surface gratings, chemical reactions on the membrane surface. Will really do in different techniques, but we really modify the surface modification using different and variety of nanoparticle and their combinations, starting from PaO2, zinc oxide, silver, CNT, graphene oxide, and many compounds. So usually you prepare a RO membrane. This is the schematic representation for preparation of your RO membrane. You have the base material as the non-woven polyester. On the top, you have the polysulfone layer. On top of it, you really have the PI polymerization, interfacial polymerization will do, and really we make the PI layer. So once this PI layer is formed, on top of it, we really coat whatever the nanoparticle which is really required. So we keep it in mind what kind of an interaction this nanoparticle will really do with respect to your pollutants. For example, like you can coat a functionalized material, obviously having a surface potential, then obviously it can interact with the pollutant or repel, attract. All these things will be really considered while selecting the pollutant. For example, case we want to give it is a nano clay, right? So we wanted to really use the nano clay which is negatively charged. We wanted to repel the anionic pollutant. For example, if you wanted to really remove your fluoride or maybe like a nitrate or phosphate, it can really repel. So obviously we can use this nano clay coating on the surface. So when you wanted to really use a flat sheet, right? So you have a base material which is really we create a pattern so that like when you apply a pressure of around 15 bar or 20 bar, the membrane should not really stick on the surface of your module. So obviously we create some pattern so that the water will really pass through the membrane, pass through the channel, and really lead to your outlet. And we also provide a spacer between the channel and the membrane, and we really prepare this membrane material, as I said before, and we assemble it and really stitch it so that it really hold on the surface properly. And we use different nanomaterials like TiNT, graphene oxide, and zinc oxide nanoparticles, for example, like of different shape, spherical, flower, and like a rod. All these varieties we prepare and we applied on this particular surface to really delay the fouling and improve the flux. So I really show you the some of the results that we have, right? So this is the AFM microscopic image of the membrane surface. So obviously, if you take an AFM image, so you can see here RA is the roughness of the membrane. So this is the prime, which is uncoated nanoparticle on the membrane surface, only like a PFC membrane without nanoparticle. The roughness of the surface is 27.08 nanometer. But when you really coat a small amount of 0.01 weight percentage, your roughness is really decreasing to 15.96. So this ridge and valley area are the place where your target pollutants, for example, like your emerging pollutants of small amount, or maybe like your other material like NaCl, will really occupy on this particular surface, and it lead to attract more pollutant and lead to fouling. So once you really smoothen the surface, obviously it won't really attract any pollutant in the ridge and valley, because no ridge and valley is really there. But if you add more and more amount of your zinc oxide particle, they agglomerate each other, then they tend to accumulate, tend to increase your roughness surface. So obviously, the idea is I need to really find out what would be the optimum amount of material which is really required to be coated on the surface. On the other side, you can see that the contact angle when it is really coated is also simultaneously decreasing. So obviously, we have to make a balance between your contact angle of the membrane as well as surface roughness of the membrane material. So I'll give you one example. This is the rejection, salt rejection is given here on top, and you have the water flux, which is really shown with respect to different percentage of ZNO contents. So when the ZNO content is really increasing up to certain level, you have the improve in water fluxes, but simultaneously there was a decline in salt rejection. But anyway, it is close to 95%. Obviously, based on your requirement, you can really choose what amount of your zinc which is supposed to be really coated. Not only that, if you really operate the membrane system for a very longer duration of time, you can see that this is black one is indication of the uncoated nanoparticle on the surface, whereas if you coat it with zinc oxide, the performance is really improved for a longer behavior, because you can see here the flux is really declining for a PA membrane, polyamide membrane without coating, but whereas for the other membrane, it is really increasing. So your cleaning period is not really, for example, like 300 minutes. It may be really delayed by another 2 hours, probably, or 3 hours. I can really take out the membrane here and I can really clean the membrane. I put it back for operation purpose. And again, this is the other example for nanofiltration membrane coated with TiNT nanoparticle. Then this is again similar way. We also find out the contact angle measurement as well as the roughness of the surface. Then you can see here the water flux when the nanoparticles are not really added, you will get only 22.8 liter per meter square per hour. But when the TiNT is loaded at very small percentage, weight percentage of 0.05, the water flux is really increased to 50.1 liter per meter square per hour. So meaning that in a given day operation, you will get 2 times the increased water. So obviously the energy required, if you calculate, it is reduced by 50%. So one can really operate this membrane by coating the nanoparticle and decreasing your energy which is really consumed. So this will really answer some of the questions raised in the previous session. How do you really save the energy? Yes, membranes are really energy intensive process, but some of this membrane surface modification really reduce the energy for total quantity of water which is really treated through the membrane surface. Right. So we also prepare the membranes for mixed matrix membrane, not the coating on the surface. We mix the nanoparticle in the recipe, and we also prepare for photocatalytic membrane reactor. This is how we really prepared it, and we operate it for small scale photocatalytic TiO2 membrane reactor. Right. So this is the lamps which is really housed for advanced oxidation process, the solution containing the emerging pollutant, other organic matter, which is really passed through, which is degraded in the reactor, and the degraded effluent will really pass through your membrane modules. So we really incorporated both photocatalytic membrane as well as your photolite, such a way that the membrane will really operate in a coupled manner. So similar way, one can also really produce hollow fiber material, and you can also study how much is the flux in the same membrane skid, and you can also apply for photocatalytic purpose. But you have to understand how much is the surface area required, what would be the percentage of TiO2 which is really required to be coated on the membrane, how much percentage of them are really exposed on the membrane surface. These are all the key things, and how much hydraulic retention time you have to really give it in the reactor to degrade the compounds, right? So all these things are supposed to be really studied. Right. The other way, we also work on membrane bioreactor. Many of you really know and understand from the previous lecture that the activated sludge process is really replaced with membrane modules to really retain the biomass. So we also have the typical movable setup for membrane bioreactor, right? The inside you have the membrane modules, and we also have the different props to measure what would be the dissolved oxygen, pH, and we can also control the other parameters of flow. Right. So this is the typical arrangement. We have the submerged membrane bioreactor we have, and the flow is really passed through the pump, and we really withdraw it at a particular pressure. transmembrane pressure, and we measure different parameters, and we also measure how much of emerging pollutant and common COD which is really removed in the reactor. So the key is this is a hollow fiber frame module which we already really applied for 1,000-liter bigger field scale membrane bioreactor. I just wanted to give an example of how the hollow fiber look like with 7,000 fibers housed in one single module. Now, when you really operate a suspended biomass inside a membrane bioreactor, all your suspended biomass which will really clog your membrane, that will lead to a fouling. So what we do in our research is we really prepare a biomass beads. The biomass is really immobilized on it's a alginate and chitosan combined with biomass of different proportions. We really prepare combining with powdered activated carbon. So by doing this, the biomass won't directly attach to the membrane material. So obviously it will delay your fouling, and whatever may be the SMP or EPS which is released at the process, which also can be absorbed by the beads. So the dual advantage you will get, the cellular materials don't really go out, but still you will perform it for a very longer time because you are really delaying your fouling. So one can also really study about the effect of different proportion of beads and how it is really the fouling is really delayed. So we also, a PhD scholar, worked in our lab and we formulated different beads like this, and we also characterized. Only problem is these beads are really not sustainable for a very longer period of time. So you need to really make some arrangement. You harvest at a shorter period, dry it, again you apply, and different batch of things you can really try here. So still more research is really needed in this particular direction here. In the other side, this is what the key focus of Professor Howe's lecture is. If you want to really reduce the energy, because mainly the membrane reactor, the energy is required from the aeration of blowers in addition to other things which is happening in commercial activated sludge process. So to make it more energy effective, so you can change to hybrid membranes. That's what we really do in our lab. So delay the fouling, increase the flux in our membrane. And we can also change the membrane from aerobic to anaerobic MBR. So exactly, anaerobic MBR will give you some kind of an energy output from your reactors. So in the form of your methane or hydrogen gas or any other gaseous substance. So this can also be utilized for passing the air to avoid your cleaning processes of your membrane. And exactly, Professor Howe discussed about this anaerobic technology. You can also produce methane gas, as well as you can stop at the level of hydrogen gas based on your requirement. But some of the questions I see that whether domestic wastewater can be really useful to produce a methane gas. Yes, it is really useful to produce a methane gas. In anaerobic digestion, 1 kg of COD really produces 0.35 meter cube of methane at standard pressure temperatures. So in the other talk, you can also see more about this particular data. I really give this. Yes, it is really possible to produce a biogas from your domestic wastewater, provided this particular COD is biodegradable and it is not creating any toxicity to the microorganism in your anaerobic technology. It may be any anaerobic technology, USB, or maybe anaerobic MBR. And the evaluation of your membrane technology, actually we are here at the current stage, activated sludge process being replaced by membrane bioreactor, UF and MF. But in the next stage, you may have nanofiltration combined with anaerobic MBR, solar disinfection, and microwave UV filtration techniques to really remove the contaminants. This is what I really wanted to tell about the membrane technology. So very briefly, I will also introduce the advanced oxidation process. If you ask me why advanced oxidation process, I put it in a simple way. To remove complex organic substances, because usually these advanced oxidation process will really come as tertiary treatment unit. So obviously you have trace organics of the complex organic compound, which is really bypass your secondary treatment will really come here. We wanted to mainly target this. And we also wanted to have non-selective oxidation of your trace organics. And you can also think about simultaneous oxidation and reduction of pollutant in your aqueous system by understanding what is the position of your valence band and context band, what compound will actually oxidize and what compound will really reduce it. You can really plan your experiment and prepare your catalyst. And if you ask me why to improve your advanced oxidation process, yes, you want to really couple your process together by means of degrading it, and also you can use it for disinfection. Once you have an advanced oxidation process, your bacterial disinfection already happened with respect to time. You no need to really go for disinfection separately. Now, improve your rate of reaction, because advanced oxidations are really popular for your increase of your K value, rate constant values, right? Obviously, you wanted to increase it. The advantage being it will really reduce your treatment time. Then other advantages, you also need to look into the support, the favorable condition for your downstream treatments. Some of your trace organics are really toxic. So for example, you want to really apply nitrate and phosphate removal by removal of your algae. That may not be possible because these trace organics may really hinder your algal growth. So obviously you need to really plan yourself and draw a schematic and really couple the process wherever you really want. And the coming days, you will have lectures more about details of each and every process. And these are on the list of advanced oxidation process. One cannot really work on all the process. So we really work on photocatalysis, piezo photocatalysis, and also we really coat piezo catalytic materials on the membranes to have a self-cleansing membrane modules. And we also work on microwave and microwave assisted process for the degradation of organic compounds. There are other processes which is really tried by many other people. You can also get a glance in the coming days lecture. And why we work for advanced oxidation, we really produce all these radicals, the predominant being hydroxyl and sulfate radical, to distract the compound. Whatever may be the AOPs, we really try to really generate this in much quantity and create an oxidation reduction potential listed here. All know photocatalysis, we input the energy and we really excite the electrons to move. The excited electrons and the whole H plus, right, proton will really do the job of oxidation as well as reduction. This is what I really talk about. So your reduction will really happen at the conduction band. Obviously, you have the oxidation in the valence band. You select the two compounds based on which compound will really feasible to really reduce and which compound will be really feasible to oxidize. And usually photocatalysis are really done with suspended catalyst. But we also work on suspended catalyst. We also really immobilize the catalyst and prepare recoverable catalyst by doing it in a chitosan matrix, right? Non-toxic chitosan matrix, and polymer, right? PBA, chitosan, and TiO2. We prepare different beads. Basically, the aim is to really retain this catalyst within the reactor. I said before, membrane or EC pre-filtration membranes will be sufficient to remove all these recoverable catalysts. But if you really wanted to remove this nano-sized suspended catalyst, you need to have nanofiltration or RO membrane module. Then again, that can really produce fouling here. So to avoid this, we really produce. Not only that, some of the catalysts may be really toxic. So obviously, you need to really stop them at the level so that you can reuse it for different cycles. And these are all some of the photocatalytic reactor setup that we have in zero decay discharge of Department of Civil Engineering, IIT Madras. This is a falling film photoreactor, right? It's just a photolytic reactor, and we have we constructed small batch photocatalytic reactor, and we also attempted to remove the removal of emerging pollutants using blue light at 454 nanometer using a catalyst like graphitic carbon nitrate. Right? We also attempted to add sulfate and produce sulfate radical. How the sulfate radical is really done in the presence of graphitic carbon nitrate and also modified with acetic acid, modified graphene carbon nitrate, and we check the efficiency. And we understand that when the sulfate radicals are not really, produce so much, meaning that we have the disposal limit for sulfate also. So obviously, like you need to restrict the quantity of sulfate radical production with the use of your persulfate addition in the beginning, such that you make not a toxic sulfate which is really going out of your reactor. And we also have the batch photocatalytic reactor and the scaled up continuous photocatalytic reactor for different photocatalytic studies. And a typical example I wanted to give you with respect to GAC, TiO2 and chitosan based graphene oxide, we tried it for the degradation of a compound like metronidazole at little higher concentration, 10 milligram per liter, aimed at hospital wastewater treatment with 30 watt 2 watt UV power. And you can see that even at the end of 15 cycles, this CS coated GAO was really producing better removal efficiency. Then there's the same thing with respect to polymer based composite like PVA CSTAO2. Still the performance is really very high at the end of the 15th cycle. So what I wanted to highlight you is, so if it is a trace organics, which compound will be really degraded? So you need to apply and find the technique and you have to do it. So for example, like we apply this photocatalytic process for TiO2 coated, bead with PVA CSTAO2 applied for metronidazole, ceftiofer, a pharmaceutical compound, and tetracycline. When these three are really combinedly present in the wastewater, tertiary wastewater, so the removal is really different for different pollutants, right? At a different concentration, each which is really 0.1 or 1 or 10 milligram per liter. So the idea being, if multiple pollutants are really present, so you have to give enough reaction time and you need to design a process for the one which is really least degraded. So that would be your target, even sorption or maybe like any other process. What compound is really least removal? That would be your design criteria for scaling up your reaction. Then coming to last phase of my research, I quickly give the overview of algal technology. If you ask me why algal technology, to remove nutrients, mostly your nitrate and phosphate in a particular ratio, you can really remove it from aqueous system, because precipitating them out or maybe like converting nitrogen into dinitrogen gas may not give you an energy input, whereas nitrate and phosphate, if it is really taken as a source by algae, the algae can really convert it into energy. So obviously convert pollutant into energy in a wastewater treatment plant and reduce the overall cost of treatment by creating some kind of a energy within the process. So why to couple algal technology with other treatments, right? To obtain a favorable initial condition for algal treatment, because that's what I said before, subsequent treatment supposed to be effective in removing the pollutant, and to meet the disposal standard for nitrate and phosphate, and also to reduce algal toxins. This area is really less researched. So obviously one can study how these algal toxins are really produced in algal reactor and what would be the fate of these algal toxins in the downstream process like membrane units, how their removal, how they are really contributing their fouling, one can really study about this. So usually when you see the mechanism of algal growth, right, algae may be like an autotrophic or mixotrophic or heterotrophic in nature. Usually like you need to identify the favorable condition for the algae, input with your nutrients, and some algae really take the alkalinity as the source of carbon. Some algae which can survive in the presence of your organic carbon. So one of my PhD students take up the leachate treatment using microwave oxidation reactor followed by an algae. But you can see here, leachate is really very rich in pollutants, right? So obviously we conducted a coagulation flocculation initially to remove some amount of pollutant. Later, the microwave is really put in place to degrade the organic matter and also strip out the nitrogen in the form of ammonia. Later, which is really given for algal processing. So we operated batch as well as the SBR type of an algal treatment. Sequentially, we really tried it, and the algae was really growing good in the microwave treated reactor. Up here, we have the coagulation flocculation process. So you can see here the biomass was really growing well in the microwave effluent as well as in the other conditions like coagulation, flocculation followed by microwave. Initially, it is really not growing, but later stages, it is really growing very well. The alkalinity is also taken up by the algae, and it can also utilize around 40% of TN as well as TP removal. But still, the performance was not really very consistent at the downstream cycles, because of the variation in the influent parameters. So one can study about how to make consistently a good performance, and algae is a key challenge which can be really addressed by any researcher who want to really take up this to use the wastewater for recycling applications. And one good thing is like we identified the energy value of the algal biomass. So the algal biomass, which is really harvested from the in this particular study, we converted the calorific value, and it has a calorific value of really 16.5 kilojoules per gram. This is what we observed. So obviously, this much of energy we recover in the form of the algae. So obviously, this particular study, the amount of algae which we harvested per liter of wastewater is really very small. Much has to be really done here. So overall, the mechanism of removal is really microwave, which is done for ammonia stripping, coagulation, flocculation for turbidity removal and organics bar COD removal. Then algae is really able to take up the alkalinity, total nitrogen, phosphorus, and zinc and iron for their metabolism. And some amount of phosphorus and copper and lead was really accumulating in the algal cells. So much to explore what condition would be really very suitable for algal cultivation. Professor Chandra will really discuss about how to construct a better algal bioreactor. And we also attempted this for hybrid treatment of distillery wastewater, which is really treated initially by electrochemical oxidation. Then we really given it for photobioreactor studies, right? This is the condition which we get from the electrochemical oxidation. 70% COD was removed, 45% TOC, 35% TN, and 95% of color removal. This wastewater is really given for algal reactor after different dilutions, and the algae could able to really perform at a favorable nitrogen is to phosphorus ratio, right? So, and also the gas which is really evolved from your any advanced oxidation process can be really captured, and which can also be really pumped in to solubilize and convert as an alkalinity, and you can really supplement for your algal bioreactor. So this is really in our earlier stage of research. One of the PhD students is really working on it, and we could able to really see that the CO2 is really captured by algae, and it could also really polish the wastewater which is coming out from electrochemical oxidation. So once the biomass is really harvested, you can really convert them for biodiesel, bioethanol, biopolymer, or hydrocarbons. And we are yet to study the algal biotoxins and their subsequent removal in the membrane process. That would be the key aim of our lab's research. And with this, I will really summarize. I would say new membranes with improved selectivity, stability, and high flux are the key requirements. And less energy consuming membrane operation and self-cleansing membrane are the future. We are looking into this future development of self-cleansing membranes by coating piezocatalytic materials. And advanced oxidation process for simultaneous removal of pollutants so that it can really remove the pollutants at a stretch, obviously to reduce the cost. And multi-pollutant removal is the key, and which is really mandatory for field scale application. And energy recovery from wastewater in any form, including the algae, should be investigated for sustainable wastewater treatment. And I really thank all my collaborators and the funding agencies and all my research scholars of IIT Madras and elsewhere, and all my collaborators, Professor Howe, Professor Lin, and Professor Gopal, and Professor Marwa and Dr. Ahmad from National Research Center, Egypt, related with the membrane work. Thank you very much. I stop here, and I'm happy to answer if you have any questions. And I take up the question from a participant, Sudalai. He's asking, like, will microplastic in sewage get filtered by MBR? If they are really greater than 0.3 micrometers, obviously, microfiltration membrane will be sufficient to really remove it. So usually people address the strategy of removing them in the sedimentation coagulation process. So obviously they will get removed there. If it is really bigger size, they will interfere with the metabolic activity of the organism in the MBR, and they create a problem. But if you see their transport through the MBR, it may not be, because they will really stop by the membrane molecule itself. So one has to study what kind of interaction the MF membrane has with respect to different category of microplastics, which is coming in your influent. So I thought, like, I answered here, I put it as answer live and done. And Akansa, how much does nitrogen in wastewater affect the membrane life in any membrane system? Does it significantly affect the OPEX towards the membrane replacement? So usually, like, this is based on the transmembrane pressure which is really generated on the membrane surface. So obviously, if your transmembrane pressure, before starting any membrane study, you have to identify what would be the critical flux and the corresponding critical transmembrane pressure. So if you operate the membrane more than your critical membrane pressure that you can really operate, obviously it can tend to create damage to your membrane module. So obviously one has to really identify what would be the critical membrane pressure, and you have to, when the membrane critical pressure is reached, you need to stop it and you need to really clean the membrane by means of backwashing the membrane or physical cleaning, or you adopt some operational strategies like on-off mechanism during your membrane, or relax cleaning. The on-off is really called as relax cleaning mechanism. You can really do during your operation. So that can delay it. So I cannot say it is only because of nitrogen and limitation. It is because of the pressure that is really generated by all the pollutants. If you have more clarification or questions, please come back. I put it as answer and done. Is membrane are costly? Is it possible to reduce the cost? So you have different polymeric membranes, because our group is really working on polymeric membranes. We are not really working on ceramic membranes. In the polymeric membrane, to my understanding, the PVDF membrane is really a little expensive because they have good elongation property and good strength, right? So elongation property and strength is really more. Obviously, your critical transmembrane pressure operation will be much higher. So these membranes are a little expensive, but it can really withstand for very longer duration of time. As per my understanding, I guess I have really answered this particular question. Madhuraj, if you have some question, please come back. What is the removal percentage of nanoparticles from treated wastewater? This is about the emerging pollutants, right? If you see the emerging pollutant, right, or maybe like dissolved solids like NaCl, their removal is close to 95 to 98% based on how much is the TDS that you have. We only tried for brackish water TDS up to a level of 5000 milligram per liter. And we also studied desalination, but the membranes were not really effective. So we are really formulating some membranes really applicable for desalination for different stages of desalination RO treatment. But if you see the nanoparticle removal, because the nanoparticle we really coat on the surface because they are really rigid and they are really resistant for a longer time. So we operate for several days of operation. After that also they are really stable. And I think I have answered this. If it is an emerging pollutant, we prefer to go for advanced oxidation first, degrade them, then send the things to a RO module, because advanced oxidation can also oxidize your microorganism. When the microorganism is really oxidized, their cell fragments and extra polymeric substances may really go along with the effluent, and that can be really retained by your membranes. So that's the key way of really making the alignment. I guess I answered here. I put done. You can come back if you have more questions. In case of higher capacities of sewage treatment, will the algal methodology remain feasible in achieving the desired output standards? Algal treatment especially take more time, right? Obviously, the HRT required will be 5 days, 3 to 5 days, and it may be longer in some cases. If you really go for large-scale treatment, yes, obviously more space is really required, and you have to really construct your algal pond in a systematic way, or tubular channeled continuous reactor you have to really construct. But I would say may not be really possible for that much high capacity. For small scale treatment, one can really do it and recover energy. So that can be really scaled up. One has to really look into it. But to my understanding, we never tried for a large scale. Our systems are really batch scale. Someone has to really take it for a bigger scale. I think with my knowledge, I answered this. What about the sludge production in the advanced oxidation process? Right? Usually, like when you really oxidize the organics, right? Some cases, you really oxidize the substances to produce sludge. But sludge production at this level of advanced oxidation will be very less compared to the conventional sludge that is really produced in your primary and secondary treatment, because the level of pollutant which we are talking about is also very less. For example, like if the metal are really producing or forming a precipitate, then obviously the quantity of precipitate which is really generated will be too less. That's what I feel. And if sludge is really generated, that sludge is supposed to be handled properly. It should be tested before really disposed to a particular place. I think how to increase the efficiency of heavy metals by photoreactor, right? If you have a photoreactor, we have not attempted the role of heavy metals on the photoreactor, but usually like the metals, some of the metals are really less soluble at their highest valence state. Obviously, when they are really oxidized, they may really form metal hydroxide and they will really precipitate. But the toxicity and most of the wastewater characteristic, if you see, obviously our goal is to really oxidize your trace organics, which is really highly toxic compared to your metal sources. If industrial wastewater or any other, probably like a groundwater which is having a specific source of metal, that has to be really given specific treatment. But we haven't looked into the effect of heavy metals, how really it is affecting. Probably we can take it up in the future. Thank you for the nice question. So how we conclude the result if contains mixture of pollutant based on the removal efficiency or any other? So usually like we study on multi-pollutant removal, right? Even in applied advanced oxidation or adsorption, because when you really get a breakthrough for a pollutant in a mixture, right? That would be your key compound. So your design is really based on that particular key compound. For example, like a mixture of 4 or 5 compound is there, right? One compound is really degraded very less percentage. So obviously that would be your target, provided if your disposal standards are really not met by that poor removal in your advanced oxidation process. So that would be your key design parameter as far as myself is concerned. Most of the algae are autotrophic. Are the significant number of heterotrophic algae? No, we are using heterotrophic algae in our lab. So they could be able to consume some amount of COD also. There are many variety of strains which is really available. So they can also take up your COD. But you cannot really ask the algae to really utilize the carbon source like any other heterotrophic bacteria. Right? So there are heterotrophic algae which can be able to take your COD to such an extent. So are there is water scarcity, but again going for dilution to treat, is it eco-friendly? I would say whatever the wastewater which is really treated, that can be used for dilution purposes. So that's the ultimate key. So you have to really decide on what would be the percentage dilution and what would be the source of dilution water. You have to really estimate. So the overall idea is I need to really reduce my cost of treatment. By adding more amount of dilution water, you are increasing the cost, then obviously it is not going to be economic. So you have to understand where would be the dilution water and what would be its cost, or you need to find out in your treatment cycle itself, then you have to identify. If you feel that like dilution again is really not cost effective, better to find out the alternate process, because it is not adding any value to decrease your cost of treatment. So you have to work on the overall schematic of your treatment plant, as well as how to really reduce the cost of treatment. I guess I answered it. If you are not satisfied, please write it again and we look for a better answer and we'll come back to you. So one last question, I will take it. Can MF membranes remove heavy metals? So microfiltration membranes cannot able to really remove your heavy metals, because their membrane cutoff size is only 0.2 to 0.3 micrometer. They are really dedicated for removing your suspended biomass, right? Suspended solids is basically retained, like your biomass in your activated sludge process or MBR will be retained by the membrane, but heavy metals will really pass through your microfiltration membranes. So obviously they are not really useful for retaining your heavy metals. Whereas heavy metal removal, you can also see in your biological systems, because heavy metal will be utilized by the biomass, and some of the heavy metals may be biosorbed. And even when you get a thin film which is attached to the membrane, obviously heavy metals can really sorb in that. So for that, because of that, some amount of heavy metal removal you can really expect. But if you see by the performance and the scientific mechanism, heavy metal cannot be removed by microfiltration membranes as such. And I tried my best to answer the questions, and thank you very much for your patient listening. And with my little knowledge, I would be able to explain the process and wherever the coupling is really required here. And I see that large number of participants still there online, and thank you very much for the interesting questions. And some of the questions are really very good. So keep participate in the question and answer session. That may be useful. And we'll write to the speakers to get the answer, and if they could not find time to answer all the queries. And I think like we'll wind up the session here and inform you. Tomorrow, our session will start at 5 p.m. IST, not at 4 p.m. So we start the session with the Professor Chai Hong Ko at 5 p.m. Then Professor Gopal Achari from University of Calgary at 6. So please make a note of the timing. You will get anyway the reminder. Please join us. Yeah, yes, Professor Lim, your lecture, Singapore time 6:30. Yes, you're right.
Okay, 6:30.
Yes, yes.
Dr. Kumar, you have very excellent presentation, quite inspiring. Yeah. So I don't know whether I should ask question because it's quite late. I'm quite impressed by your photocatalytic reactor. Yeah, which is quite large in scale as compared to other labs I've seen. Okay. For the continuous system, do you recirculate the permit or you actually let it run?
Yeah. For this reactor, we haven't recirculated it because we wanted to find out the efficiency for a given HRT. So we didn't recirculate it back.
Okay, that's good. That's good. Yeah. I believe you have encountered with papers on LED. You LED instead of the
not LED. We haven't used the LED yet. We are actually planning to use in our forthcoming experiments to compare how the normal UV and LED.
If you use LED, based on my experience, LED A is not that damaging to the polymeric membrane. But of course, nowadays the price for LED is still expensive as compared to traditional mercury lamps.
Yeah. So I hope you discuss more aspect of this in your lecture.
Yeah. No, I won't cover photocatalytic. I think you guys have done a very good job. I stopped on that, but I moved to the other kinds of AOP. Yeah. Okay. I will share with the audience on Monday.
Sure, sure.
Yeah.
Thank you.
Okay. Yeah.
Thank you.
Bye.
So I think we stop for the day if no more question. Professor Lim, thank you very much for your patient hearing and take your time out of your busy schedule and being here. Professor How, you're still here. I'm really happy that you would also be here till the end. And I also see the Siren Fang, your PhD student UTS. And thank you very much. And thank you very much for all the participants. And Professor Ho and Professor Lim, shall we close for the day and we'll start the session tomorrow? I think, Professor Ho, it's already late for you. I think like you're muted, both of you.
Yeah, tomorrow I have a late appointment throughout the whole evening, so I probably have to skip. If possible, I will just come in for a short while.
If you're available, then please join. The link will be active.
I hope that I have time during this period, but actually my time is also quite packed. Yeah, that's why I scheduled my talk on Monday. That is only available time for me next week. Okay. Yeah.
Thank you very much. Thank you. Bye. Thank you, Professor Howe. And I think with all your permission, we'll stop the session here. Thank you very much. Participants, please join tomorrow at 5 p.m. IST. Thank you very much. Have a nice day.